Good morning and welcome to today's session. In this session we are going to discuss Gibbs sample, and I am using an orange Ventrace algorithm to compare Gibbs sampling. Agenda: the concept of best from available, an analogy of orange Ventre, and formal algorithm, and finally applications. Our goal is to collect only those samples best from available, as the oranges picked by a vendor from his basket. So to understand this Gibbs sampling, I am using an example of selecting oranges by a vendor from his basket. Consider an orange vendor who serves his service near the footpath. I just visited him and asked him 2 kilos oranges. That is our initial step. We just joined him and asked for 2 kgs of oranges. So he select a packet and he knows how many oranges required to come up to 2 kgs. For simplicity, I take it as 12 oranges. How he select oranges from his basket? As we know, first we choose the most reddish orange, because if that orange remains in his basket, the next day he has to throw it into the waste basket. It will stale. The reddish oranges is actually the old stock. So the first orange he select is the most reddish and he transfer it into my packet. Then he just look into the remaining oranges in his basket and select next reddish one. At the same time, he keep it in mind that one orange is also put in my packet. The remaining is only 19. He make use of that knowledge. Now select the next reddish orange and put it into my packet. Then he select next one and he do it until he got 20 oranges. This is the way. So he select conditionally. He used 2 conditions. One is the number of oranges he is going to select, and second one is the best available. Here in the sense of best in terms of his profit, not in my profit. So he select most reddish orange at each time, and so he select oranges in this way from his basket. Now we try to make connections. These are the 4 points I would like to tell you. One is select from the available best in source. Best means up to his choice. Okay. Second one is can collect one by one or in batches. The vendor can collect oranges one by one, or he can pick 3 or 4 simultaneously and put it together in our packet. No problem. It is allowable. Next is each orange will have imprint on the strategy. He use a conditional selection. That conditional selection is imprinted in the orange because the first orange is the most reddish. Then it come more better or fresh items will come to my packet. That's all. So the freshness is actually initially very low, then freshness level increases gradually if you draw the freshness in a sheet of paper as a graph. Okay, so that selection strategy should have an imprint in this selection, in these oranges, the selected into and put it into my basket or my packet. On the limits, the sample will have the quality of best in available. That is actually happening. If he follow this procedure or follow this strategy, automatically the old items will be sold fast. So what happened? He will get the best in available. Fresh items will be in his basket at the end of the day. He is the selector. That is why this is the best available policy for him. Now we are going to connect this into my Gibbs sampling. I am going to formally define what is Gibbs sampling. It is also a probabilistic sampling approach that is used to create best available samples from a population. See, it is best available selection process. I think you may remember the MCMC. In the case of MCMC, it is the best fit selection. It is not best available. So Gibbs sampling is best available. So conditional selection is used here. Now this is the formal algorithm. Don't worry about this algorithm. It is very simple. We can connect our orange vendors example to the selection. First of all, as in the case of the orange vendor story, we fix how many oranges are required. Here in the place of orange, you think about our samples Z1, Z2, etc. Zm. That means we need only m samples at the next state. First of all, I select the first element or first sample, that is Z1. That is in the tau plus 1 state. We start from the current state, that is tau. That is we approach when we are approaching that vendor, that is our current state. When he start selecting a kit and put oranges into that kit, that is the tau plus 1 state. Like that. Think like that. It's very simple. So Z1 tau plus 1. The first one is selected in tau plus 1 state. That follows this distribution. You just keep this probability for this time. Now think about this interior portion. I am selecting conditionally. I select Z1 with respect to the remaining Z2, Z3, etc. Zm. That means I select the reddish one compared to others. Think like that. That is in the tau plus 1 state. This is the probability distribution. We are taking the probability for that, the chance for that. That is actually he trying to search the reddish orange in his basket. That is actually the probability distribution. Now I have Z1 in my packet in T plus 1 state. Now I am going to select second one at the same state, Z2 T plus 1. Now we have to consider two conditions. One thing, I am already selecting Z1 in tau plus 1 state, and I am considering the best from available remaining items or remaining sample points. That is here. First of all, I consider the selected one Z1 at this tau plus 1 level. Now we are going to select Z2. Now we consider the remaining one Z3 tau, etc. Zm tau. So now we have the second sample. Now I am going to collect the third sample Z3 tau plus 1. Now we have to consider both things. One is I have selected already two elements, two samples Z1 Z2, that is in tau plus 1 state, that is conditional, Z1 tau plus 1, Z2 tau plus 1. Now here think about the remaining. Remaining means we are selecting, this is not Z1 Z3, we are selecting remaining, that is Z4 tau, etc. Zm tau. We continue like this, and finally I am choose the last one, that is mth item. Zm tau plus 1 is equivalent to, that is distributed probabilistically P of Zm. I select Zm such that already m minus 1 elements are in my packet, that is Z1 tau plus 1, Z2 tau plus 1, etc. Zm minus 1 tau plus 1, and I am choosing the last one. There is no conditioning on the available thing because I am selecting the last one. We think about already selected points. So when we follow this process one by one, we got a very good distribution. This is the best available probability distribution. What is known as a conditional selection because this is a conditional probability. It's a good algorithm for machine learning and also for deep learning. Okay. Now one more problem is if we are selecting items one by one, it is more time taking. So reduce the time, we can select more elements together. That means in like blocks or in batches. So batch Gibbs can be achieved in blocking Gibbs sampling algorithm. We arrange Gibbs sampling in terms of blocks. We select 3 or more similar things together, then put it into the bag like that. By choosing blocks of variables, not necessarily disjoint. Disjoints, if the samples are disjoint, it's very easy to calculate the joint distribution. If the disjoint property is not there, we have to apply the multiplication property in probability, nothing else. And then sampling jointly from the variables in each block in turn, conditioned on the remaining variables. So we take 3 oranges together, then it considers as one block, then apply conditioning on the remaining block. That means we put oranges in small packets, then put the packets into our scale and weight it and put into new kit like that. This type of sampling is also known as batch Gibbs sampling. It also reduces the time required to complete the sampling, and also there are some other advantages like in probability calculations it will minimize the effort in marginal approximation. So the important applications of Gibbs sampling are, the first one is used in natural language processing. That means from the available words we are going to create the best possible sentences. So sentence making or sentence creation problems in NLP, Gibbs sampling can be used. Second one is probabilistic selection models. We can use Bayes models or Bayesian models in probabilistic machine learning with the help of Gibbs sampling selection. These are two popular applications of Gibbs models. Thank you very much.